Our next problem is called permutation of string. We are given two strings S1 and S2. We have to return true if S2 contains a permutation of S1 or false otherwise. In other words, we have to return true if one of S1's permutations is in the substring of S2. So for example, in the example 1, we have S1 is equal to AB, and we can find the permutation BA here in the string. So S2 contains a permutation, we just return true. In the second example, we have A and B, but as we can see here, we never see AB or BA in the string. Like we don't have a consecutive AB and BA in the S2 string, so we just return false. The constraints are that S1 length and S2 length are from 1 to 10 to the 4th, and S1 and S2 only consist of lowercase English letters. Now, the brute force solution for this is to generate all the permutation of S1, and then for each permutation, check if it's a substring of the S2. But this will not work for any reasonable strings like that have a length more than 30, for example, because we will have to generate all the permutation of S1 and then also do the computation for the substrings, which can be possibly done in the linear time complexity. So finding a substring can be done in linear time complexity, but generating the all the permutation would take n factorial. So we would have the brute force solution will just not work here. But the thing that we have already kind of faced is that for permutation, searching for permutation, a good thing to know is the frequency of the characters. And to calculate the frequency of characters, we are always using the frequency map. One additional helpful thing for us is that we only have lowercase English letters. So we know that we will have a bounded frequency map because we can map all the lower English letters to an array of 26 elements, because in total we have 26 English lowercase letters. So we can have an array of 26 elements, and then we can map whenever we find a character, a letter inside either string 1 and string 2, we can just increment the value at a certain index that corresponds to that letter. So for example, if we have a letter A, then we will just increment the value that we have at the first position, first element, so the index 0 in the frequency map array. So that's the first thing. Now, how does that help us to find if there is basically the permutation of S1 is a substring of S2? So we will solve this problem by using something called fixed sliding window approach. So basically, we know that S2 is larger, because if it's not, then we immediately return false, because we are searching for S1 permutation as a substring S2, not the opposite. So we have S2, and we'll just use the second example. Actually, the first example. So we'll have EID, B, A, and then we'll have 3 rows. Initially, we will start, and then this is basically S2, and then we will have S1. And why is it called fixed? In this case, it's fixed because we know that if there is a substring that matches a permutation of S1, it has to be of the length S1, because it has to contain all of the characters. So in this case, we will have a sliding window of size 2. And sliding windows, we perform sliding windows by starting first with the first 2 elements of the string that we are performing the sliding window on. In this case, is the string S2. And why is it the length 2? Because basically that corresponds to the length of S1. And so the first 2 characters will be E and I. And then we will iterate over the first 2 letters of the string 2 and the first 2 letters, which is basically the whole string S1. And for each letter that we find inside the S1, we will basically increment the frequency map. So in this case, we'll increment A to 1 and B to 1. And for each letter, that's the number of letters that we have to find. And for each letter in the substring of the string S2 corresponding to the length of S1, we will decrement. So in this case, we will have E equal to -1, because the default value of all the elements in the frequency map will be just empty integer array, so all the values will be 0. And then I will be equal to -1. Then basically for each window, each sliding window that we have, and then we will have basically n sliding windows, and actually n minus the length of the S1. So in this case, n minus 2. But we can say the total number of windows that we will perform this operation on is n. So for each sliding window, we will basically check if all of the numbers in the frequency map are equal to 0. Because if they are equal to 0, that means that they are same frequency of letters that we find in S1 also present in S2. Because if we had, for example, luck here and we had the letters B and A, then for B and A, we would basically just decrement this frequency to 0 and this frequency to 0. And then when we check all of the, basically all of the frequencies will be 0, and we know that this sliding window, this fixed sliding window contains all of the elements in the same frequency as S1. So basically that means that window of the substring S2 corresponds to the permutation of S1. But because we don't have it here, we have to keep moving, and we are always keeping the fixed sliding window, and we are moving to the right. So we are always moving by one space. But before we move, we know that we don't longer have the letter E, because we are moving away from it. We are shifting this to now contain the letters I and D. So we have to perform the following. First, we basically have to increment the numbers of the letter that corresponds to the letter that we just omitted, which in this case is basically the letter E. So we just increment it to 0 in this case, because -1 plus 1 is 0. And then we have to include this letter D. So in this case, D will be equal to -1. So because we have an additional, so basically in every letter that we have in the window, in sliding window in S2, we are decrementing the frequency map. So it can combat basically the frequency that is present in S1, because for S1 we are always incrementing. So it's like plus and minus, we are trying to converge to 0 basically. So in this case we have I and D, and then when we check, we still don't have all the values in the frequency map equal to 0. So in this case we have 1, 1, and then we have 0 and -1, and then again -1. So some of the values are just not 0. So then we will move again. So now we are skipping our letter I, and we are moving to this. So we'll have D and B. So we have to increment I. In this case, it will be 0. And we have to decrement, in this case, B. So now B becomes 0. So in this case, we only have two values that are not, when we check the second time, we only have two values that are not 0. So we have the value for A and D that are not 0. Next time when we are skipping D, we are moving our sliding window. So we are including our B and A. So because we are skipping D, we have to increment it. So it will become 0. And now we are including A, so we have to decrement it. In this case, when we check, all of the values will be now 0. So we know that the current sliding window, which is BA, has the same frequency of letters that the S1 has, because we have all zeros inside. Basically, all of the frequencies cancel each other out. So here we have -1 and -1 corresponding. Actually, we are presenting S1 as 1 and 1. So we are incrementing, and here we have -1 and -1. And for all the others letters, we have 0, because the sliding window only covers these two letters. So these two will cancel each other out, and we'll get 0 for these letters too. So we can just return true in this case. First, we'll declare a frequency map, which will be just an array of 26 elements corresponding to the frequency of all lowercase English letters. Now we will also declare the L1 and L2 to be the corresponding lengths of S1 and S2 strings, and then we will check if L1 is larger than L2. In that case, it doesn't make sense to check for the permutation of S1 and S2. We just return false. Otherwise, we will basically traverse the L1 string, and for each of the characters that we find in S1, we will increment the frequency map, and the corresponding index in the S2 for the letters that correspond to the letters in S2, we will just decrement. So that's basically our first initial sliding fixed sliding window. So we will check if the frequency map contains all zeros, and if it does, we will just return true. We will implement the found function later. Then if you don't return early, that basically means that we have to move our sliding window, and we move it starting from the L1 because we have already crossed L1 elements by checking the first L1 elements in the first for loop, and you are traversing as long as I basically in a smaller than the length of the string S2. Then for each element, and then for the element that we are that we are including in the window, that's the element it's contained in the window in S2. We will decrement as we did for the characters that's found in S2 in the first for loop. But for the element that we are leaving, the first letter in the previous sliding window, which we can get by just decrementing the current index by L1, we will increment. Basically, because we no longer have this letter. This corresponds to the incrementing the letters that we have found in S1 in the first for loop. Then we will check again if we found the right sliding window. So basically that means that the frequency map will only contain all zero values. So we just return true. Otherwise, if we have crossed all these sliding windows and we didn't find this frequency map that contains all zeros, so we didn't find the permutation of S1 and S2, we just return false. Now for the found function, it will just accept the array, which will correspond to the frequency map. It will iterate over all the elements in the array and check if the value is not equal to 0. If it's not, it will just return false. But if it is, if all elements are equal to 0, it will just return true. Now note that this function will always be constant, even though we have a for loop. It will be constant because we have a bounded frequency map that only contains a constant number of elements. In our case, 26. So the time complexity will be basically linear, and for the space complexity, we will have constant space complexity because we are only storing 26 elements.